Two invisible bubbles are steering the sun's next million years. They are real cavities of hot gas shaping our sky. You can picture them as overlapping soap shells in space. Here's the immediate takeaway: our neighborhood is not empty. It sits inside a carved-out zone with moving boundaries. Tonight, we tour that zone and the giants nearby. We will meet Spica, a restless double star beating fast. We will cross Sco-Cen, a nursery that launched supernovas. We will catch a runaway star plowing a glowing wake. We will even pass a neutron star bending the vacuum. By the end, your mental map will feel local. Start by standing with me inside a dim stellar alley. The local bubble is a low-density cavity around the sun. It matters because this bubble shields and funnels interstellar material. Old supernovas blasted this region, heating gas and sweeping dust. Their shock waves overlapped, leaving a hot, thin interior behind. The walls are denser, cooler clouds that reflect and absorb light. Our path through it changes what the heliosphere runs into. That changes cosmic rays, tiny dust flux, and incoming atoms. Now for the gentle twist, the bubble is not alone. Next to it, the larger loop I superbubble bulges outward. Loop I likely grew from Scorpius-Centaurus winds and explosions. Its skin glows in radio and X-ray maps of space. Picture two soap films touching, their seam makes a corridor. The sun drifts a little each 1,000 years, always moving. Calculations suggest it will enter loop I on megayear timescales. That crossing will slowly remix the heliosphere and sky brightness. No sudden change, just a long slide through different gas. Example in real terms, starlight colors shift with dust density. Maps show the local bubble spans several hundred light-years across. The near wall sits a few hundred light-years from us. Inside, newborn stars sparkle along the walls like dew. So the picture is a warm cavity, nudging us gently. How do we know any of this without leaving home? Gaia measures star positions and motions with exquisite precision. Parallax is the tiny shift Gaia sees as Earth orbits. From that shift, distance drops out with simple geometry. We care because distance turns star colors into dust maps. Combine distances with reddening and you get 3D dust. Starlight passing through dust turns slightly red and dimmer. Millions of measurements weave a tomographic map around us. Researchers then fit shells and cavities that match observations. They trace the same bubbles seen in X-ray and radio. Example, a 3D map revealed baby clusters on bubble walls. Those clusters light up the rim like city lights. Tiny test, imagine removing 1 million reddened stars from models. The bubble edges fade, proving the structure needs that dust. The method is not mystical, just statistics and geometry. Net result, we hold a neighborhood atlas with depth. It lets us place the sun inside its real context. Bottom line, mapping turns poetic sky into measurable terrain. Shift your gaze toward Virgo, where Spica flashes electric blue. Spica is a tight multiple system anchored by two hot stars. That means two massive B-type suns whirl around each other. You should care because gravity here is on full display. Their pull squeezes each star into a slightly egg shape. As they orbit, their surfaces stretch and brighten unevenly. Spectra show lines sliding back and forth with the dance. Those shifts reveal their speeds, masses, and orbital period. The pair circles in just a few days, very close. Tidal forces churn their envelopes, mixing fresh fuel inward. That keeps them bluer, hotter, and shining in hard ultraviolet. Spica sits near the seam between our two local bubbles. The surrounding gas scatters ultraviolet light, carving faint arcs. Example in real terms, Spica floods nearby dust with glow. Space telescopes capture that soft halo wrapped around the star. Its distance lands a few hundred light-years from Earth. The primary weighs roughly 10 solar masses, the companion less. Both will end life violently, likely as core collapse remnants. Future shock waves could sculpt the very bubbles we cross. Common mistake is thinking bright means close and simple. Bright here means powerful, fast, and physically complex. So the picture is a stressed duo straddling a boundary. They mark the place where local structure meets stellar drama. Spica is a lighthouse on a changing interstellar shore. Now sweep south to a sprawling stellar association, Sco-Cen. An association is a loose family of young, massive stars. It matters because their wins and deaths shape our neighborhood. Sco-Cen has 3 subgroups, each with different ages. They span roughly 5 to 20 million years across. Winds from O and B stars blow vast cavities in gas. Supernovas then punch and enlarge those cavities into superbubbles. Layer by layer, shells stack, merge, and ripple outward. Those ripples connect directly to loop I around us. Example, the Coalsack appears as an inky patch against stars. It is a dense dust cloud, not an empty hole. Starlight behind it is blocked, leaving a black silhouette. Photons scatter off grains at its edges, glowing faint cyan. Deep inside, cold molecules rest, waiting to collapse. Some parts will ignite new suns over future millions. From Earth, the Coalsack hangs near the Southern Cross. Its distance is several hundred light-years, roughly Sco-Cen turf. Gaia ties its motion to nearby young populations confidently. Rule of thumb, dark patches usually mean foreground dust. Count on that when reading the Milky Way's mottled river. Bottom line, Sco-Cen built the local landscape with force. Its clouds and holes are the scaffolding of our sky. Swing east to a rogue sprinter, Zeta Ophiuchi. This star is a young, massive blue giant on the run. Runaway means it moves much faster than neighbors through gas. You should care because speed here writes light into arcs. As the star plows ahead, it drives a bow shock. Gas in front compresses, heats and glows in infrared. Dust grains pile into a sickle shape, curving around. Infrared images show the arc sweeping like a golden visor. The star likely got kicked when its partner exploded. Losing a companion unbalanced the orbit and flung it out. Its space velocity sits around 20 to 30 kilometers. That is supersonic in the thin interstellar medium. Example, NASA images measure the shock a few light-years wide. The arc brightens where density spikes and dims in voids. Common mistake is thinking shocks need thick air. Even wispy gas makes a crisp shock at these speeds. So the picture is a blue spear with a glowing shield. Motion, wind, and dust team up to paint that shield. Now shrink everything to city size and pack a sun inside. A neutron star is a collapsed core left after a supernova. We care because these objects push matter and light to extremes. The closest known isolated one sits a few hundred light-years. It glows softly in X-rays and faintly in visible light. Magnetic fields, there are trillions of times stronger than Earth. Electrons and photons behave differently in such brutal environments. Here comes the wild part, the vacuum itself turns birefringent. That mouthful means empty space acts like a polarizing crystal. Light leaving the surface gains a preferred polarization direction. Astronomers measured that polarization with sensitive instruments. The result matches a prediction called the Euler-Heisenberg effect. It is a quantum electrodynamics correction to Maxwell's equations. In strong fields, virtual particles tweak how light propagates. Mechanically, the field alters vacuum permittivity and permeability slightly. Example, the star RX J1856 shows a high polarization fraction. Numbers hover around 15 to 20% in optical bands. That is difficult to explain without vacuum birefringence included. Instruments also clock its tiny parallax, fixing the distance. With distance known, models of temperature and size tighten. Tiny test, rotate the polarization filter, the signal stays. Background stars do not repeat that pattern, strengthening confidence. So the picture is a compact ember that edits empty space. Physics textbooks meet the sky, and the sky answers yes. Aim into Taurus where a V of stars forms a face. That V outlines the Hyades, our nearest rich open cluster. An open cluster is a family of siblings born together. It matters because siblings let us test stellar evolution directly. They share age and chemistry, so differences reveal mass effects. Hyades shines at roughly 150 light-years away. Its age is about 600 million years by models. Gravity still binds the core, but tides strip the outskirts. Long streams of former members trail like faint comets. Gaia traced those tidal tails stretching across the sky. Inside the cluster, subgiants are peeling off the main sequence. Redder, cooler stars dominate the count at lower masses. Example, Epsilon Tauri, also called Ain, swells as a giant. Ain even hosts a giant planet with several Jupiter masses. That planet orbits in hundreds of days, bathed in orange. Meanwhile, white dwarfs mark the fates of heavier siblings. We weigh the cluster by tracking motions and dispersion. Rule of thumb, faster spread means weaker binding today. Hyades shows both a dense heart and long evaporating arms. Common mistake is placing Aldebaran among the members. It only sits in the foreground, sharing the same line. So the picture is a living lab for stellar lifetimes. Shared birth, shared motion, and shared chemistry make clean tests. Hyades turns theory into numbers you can point at. Slide northeast to a tight, blue jewel box, the Pleiades. This cluster is a younger sibling group, still bound and bright. Youth here means about 100 million years of age. We care because young stars show disks, spins, and activity. They calibrate how magnetism and rotation change with time. The stars are hot B types and cooler companions. Their blue light reflects off surrounding dust like smoke. That is a reflection nebula, not gas they exhaled. Encountered dust happens to be crossing the cluster today. Long exposures reveal curling filaments around bright members. Example, Alcyone sits as the bright anchor near center. It is a hot B star with a fast spin. Spectra show broad lines from that dizzying rotation. Nearby, many members still host debris disks of rocks. Infrared surveys count belts where future planets might grow. The cluster's distance is roughly 440 light-years. Proper motions keep the group tight against the background. Mechanically, gravity plus shared orbits hold the pack together. Over time, tides will peel members away into streams. Common mistake is calling the blue haze a gas cloud. It is sunlight on dust like headlights through fog. So the picture is a sparkling swarm wrapped in silk. It showcases youth, spin, and dusty building blocks nearby. The cluster feels close enough to almost reach out. Those two invisible bubbles still frame everything we just met. They steer sunlight, starbirth, shocks, and even quantum experiments. We walked from Spica to Sco-Cen and past a bow shock. We peered at a neutron star that polarizes empty space. We toured Hyades and the Pleiades, families evolving together. The thread remains, our local sky is structured and alive. If this map clicked for you, stick around for more. I post deep dives that keep your space sense sharp. Tap subscribe to catch the next step on this tour. Until then, look up and picture the bubbles guiding us.